So when I was in college, one of the hottest new things in the theory of signal processing and mathematics was wavelets. Uh, Wavelets are a transform that was developed simultaneously by people in filter bank theory, in signal processing, such as Georgia Tech's Mark Smith, and also by people in mathematics, such as Ingrid Dabashi's. And the two communities found each other sometime in the mid-90s. But wavelets are a really powerful tool for signal representation, so let's get started. So the Haar wavelet is, I guess, the simplest one. It's for signals in L2 over the whole real line, and it breaks down a signal by looking at the difference between piecewise constant approximations at different scales. So we'll look at an example in just a moment, but first a little bit of notation. We will let this script V0 be the space of signals that are piecewise constant between integers. So for such a set, we can basically define V0 of t to be 1 just between 0 and 1. And it should be pretty obvious that we can have shifted versions of this. That would make a good sorry. 1, 0, 1, t, v naught of t. Okay, so this would shift the versions. This would make a nice basis. And so we can then say that v naught t minus n, where n's an integer, is an orthobasis. For v naught. And because this gets a little bit burdensome to write, we're just going to say 0 comma n t minus n is equal to phi 0. I'm sorry, 0 n of t is equal to phi 0 of t minus n. Like so. Okay, so here's an example of a signal that might exist in this space. not very interesting for most things that we have to, with which we have to do, but we'll get there. And it, as I promised, eventually we're going to get to a place where we have a basis for L2 on the whole real line. But let's start with an example of how we build this up. So we can project an arbitrary x of t onto v0 as simply x hat naught of t is equal to the infinite sum. We use the standard inner product here. Of course, you can use any inner product that you wanted, but standard one is standard for a reason. It's generally more useful, more related to physical things. And so we take the inner product, and we might have something like this example where we take our signal x of t and we find the average values at integers. So I've denoted those with dashed lines here. And the average value just comes from projecting that segment onto a constant. So that's where that comes from. And the result is x naught of t hat living in our v0 space. Now, this expression we have up above for x hat naught of t is a little bit long, and we're going to be doing lots of operations like this. So let's introduce some notations to make this more compact. Let's see. More compact notation, and we're going to say that this is x hat naught of t is equal to this projection operator onto v naught of x of t. So this is performing that function that we have up above as a sum, and this returns the output of this is that signal in v naught that is closest to x of t. Okay. Well, we talked about wavelets breaking down a signal by looking at the difference between piecewise constant approximations at different scales. So all we've looked at so far is a single scale and a single piecewise approximation at that scale, and we call it x hat of v naught, or x hat naught of t, and its projection onto v naught. So now we're going to define our the next levels, I guess. So we have our wavelets. like so. So let's define this space here as, okay, so Vj is the space of piecewise constant functions, just like V naught, but at a higher resolution. So Vj contains signals that are constant on intervals of length 2 to the negative j. So as j increases, we're looking at finer and finer approximations, or shorter constant intervals. So this is what that would look like. If I had a signal on V1, you can see it now changes at every interval of 1/2. And on V2, we're looking at transitions at multiples of 2 to the negative 2, or rather 1/4. Okay, so we would like to find an orthonormal basis for this. So let's just start with an orthonormal basis for our V1. It's going to be non-zero from 0 to 1/2, and then 0 outside of that interval. But what's the height? Well, in order for this to be orthonormal, let's put this as A, we would have to have 0 to 1/2 of A squared dt has to be 1. And that's equal to A squared t, and 0 to 1/2 is equal to 1/2 A squared. So A has to be square root of 2. So instead of being a height of 1, it's a height of the square root of 2. And in general, I think it's easy to see that if we have phi j of t being the basis for, well, actually it's the shifts that are basis, and we'll get into that, but the foundational element for the basis of Vj is going to be 2 to the j over 2 phi naught, but now we're going to squish it. So how do you make a function more compact? You multiply its independent variable by something larger than 1, and that's exactly what we're doing. So we are going to use this to build up a basis for Vj. So, building this basis is going to be just like we did before. T is equal to Vj t. Now we wanted to do an integer, but we can't do an integer anymore because it's not an integer width. So we actually scale our integer by 2 to the n. And so that's going to be 2 j over 2 phi naught 2j t minus n. Okay, I'm going to try to be, just double checking here. I'm going to fix my j's. This is important. J is often used in these things, and often in signal processing we use J differently. So here J is an index. I will use that J to be the square root of -1. Hopefully they won't become confused. We don't tend to use them in a manner that is confusing, but I'll try to maintain that difference in notation. Okay, so this Vj of n t forms an orthobasis for that. One other little notation thing before we move on. If we start out as we do, with our phi naught of t. When we go to phi 1 of t, we end up with something like this. This is phi 1 of t, and that's the square root of 2, and that's 1/2. So we, the notation, or not the notation, but the vocabulary we use here is that we obtain our orthobasis for Vj by contracting, as you can see, the basis for V naught by a dyadic factor. So you'll see the word dyadic showing up in reference to wavelets, and it's talking about the fact that you start with something at one scale and you continually rescale it by this factor to get bases for finer and finer scales. So that's it. Actually, let me show you, before we end this lecture, just a brief illustration of how this works with some figures. Okay, so let's look at some Haar scaling spaces here. We're starting out with a signal here that is constant on, let's see, intervals of length 1/2. So these functions are respectively, this is at level 1, j equals 1, and this is a negative shift of 1 unit, No shift here, so that's phi1 comma 0, phi1 comma 2, and phi1 comma 3 of t. Okay. And then over here we have a signal in V1. So notice the height on these signals. It's almost 1.5. In other words, it's square root of 2. So those are our basis functions. So moving on down, we have a signal in V2. So this would be whatever we might have. X hat 2t exists in V2. So it's piecewise constant on intervals of 1/4. And so we have here V2 comma n of t for n equals -2 to 5. So if we look on this axis, the first one is n is -2, -1, and then here's kind of our base or mother function. 1, 2, 3, 4, 5, and each shift just shifts at the width of that function. And you notice, although it might be a little bit harder to see, the height of these is 2. Okay, so we're getting finer and finer, and let's see how this plays out in practice. So if we started with an x of t looking like this really strange waveform, then what we get in V0 is a very coarse approximation to this. And x hat 1 of t exists in V1. X hat 2 of t is starting to look a little bit better. X hat 3 of t. X hat 4 of t. Now you notice that this is getting fine really quickly, and that's because we're dealing with powers of 2. So the first one, x0, is on integer intervals, and 1/2, 1/4, 1/8, and 1/16. So it's getting closer to where we'd like to be. So this maybe shouldn't come as a surprise, but this is very similar to what you might see in calculus, where, for example, when you're taking an integral of something, you approximate that integral as the sum of piecewise constant function-based areas. Now, your Riemann sum is based on this piecewise constant idea, and then as the width of that sum gets infinitely small, you get something that converges to the true area under the curve. And so this is basically the same idea, only we're not actually finding an integral or anything, but we are saying that if we start with a piecewise constant function, but the pieces get smaller and smaller, infinitely small, we actually reach the function. So in the limit, as j becomes large, we converge to x itself, for any x in L2. So that's the starting part. Although I promised this was about wavelets, we haven't really gotten to the wavelet part of it yet. We've just gotten to the function approximation part. We're going to hit the wavelet part on our next lecture.